Hello, my young chemists. Let's begin with a question. Have you ever wondered how your jewelry gets its shine, how the wires in your home are purified, or how we extract aluminium for aircraft? The answer is one magical process: electrolysis. Electrolysis is not just a lab experiment with glowing bulbs and bubbling solutions, it is the backbone of industries. Its applications fall into three main categories: electroplating, electro-refining, and electrometallurgy. Electroplating is like giving a metal a protective jacket and a stylish makeover. Electro-refining removes impurities like a chemical dry cleaning service. And electrometallurgy? That's the heavy machinery that extracts metals from their ores. Each of these uses electricity to bend atoms to our will. Amazing, right? Now let's zoom in on electroplating. Imagine a rusty iron spoon. Not very appealing on the dining table, right? But coat it with a layer of nickel or silver and suddenly it shines like a treasure. That's electroplating. Here's the trick: the base article, like iron or brass, is always made the cathode. The superior metal, like nickel or gold, is taken as the anode. When current flows, the anode dissolves and deposits a thin, smooth layer onto the cathode. This prevents corrosion, rusting, and gives the article an expensive appearance. For instance, brass plated with silver becomes not just beautiful but also more durable. So, in short, electroplating makes our everyday objects both long lasting and stylish. Chemistry meets fashion. Let's dive into some specific examples. First, nickel plating. The electrolyte here is aqueous nickel sulfate. At the cathode, Ni2 plus ions gain 2 electrons and deposit as metallic nickel. At the anode, nickel atoms lose electrons and dissolve back as Ni2 plus ions, keeping the solution balanced. Now, let's compare this with silver plating. The electrolyte here is sodium argentocyanide, that's now AgCN2. At the cathode, Ag plus ions gain electrons and deposit as silver metal. At the anode, silver atoms dissolve back into ions. But why not just use silver nitrate instead? Well, sodium argentocyanide gives a smoother and more controlled deposition, which is perfect for decorative coatings. So, whether it's your cutlery or your fancy jewelry, these electrochemical reactions are happening quietly to give them their shine. Remember, electrolytes aren't just solutions, they're the recipe ingredients for the perfect metallic coat. Alright, let's move on to purification, electro-refining. Imagine you dig up copper ore, refine it chemically, and still get impure copper with unwanted friends like zinc, iron, or silver clinging to it. Not very useful for delicate electrical wires. So here's the chemistry fix. We use an acidified copper sulfate solution as electrolyte. A thin sheet of pure copper is the cathode, and a thick impure block of copper is the anode. At the cathode, copper ions, Cu2+, gain 2 electrons and deposit as pure copper atoms. At the anode, impure copper atoms lose electrons and enter the solution. Impurities like gold and silver don't dissolve, they just fall as anode mud at the bottom. This mud isn't waste, it's a gold mine, literally. That's how we get shiny, high purity copper for wiring and valuable metals from the sludge. Electro-refining is purification and treasure hunting in one step. Now comes the heavy-duty application, electrometallurgy. Some metals like potassium, sodium, calcium, magnesium, and aluminium are so reactive that no chemical reducing agent can bring them out of their compounds. Enter electrolysis. For sodium, fused NaCl is electrolyzed. Sodium ions gain electrons at the cathode to form sodium metal, while chloride ions lose electrons at the anode to form chlorine gas. For aluminium, alumina, Al2O3, dissolved in molten cryolite is electrolyzed. Aluminium ions are reduced to aluminium metal at the cathode. For less reactive metals like copper or silver, we can simply use reducing agents like carbon or even thermal decomposition. It's like a tier system: the more reactive the metal, the more energy we need to extract it. Without electrometallurgy, we wouldn't have aluminium planes or sodium street lamps lighting our roads. Now let's piece it all together with some exam-ready examples. For molten lead bromide, PbBr2 dissociates into Pb2 plus and Br minus ions. At the cathode, Pb2 plus gains 2 electrons to form lead metal. At the anode, bromide ions lose electrons to form bromine vapors. In acidified water, H2O and H2SO4 dissociate into H plus or minus and SO4 minus. At the cathode, H plus ions gain electrons to form hydrogen gas, while at the anode, or minus ions lose electrons to form oxygen gas. Notice the volume ratio of hydrogen to oxygen is 2:1. Finally, in aqueous copper sulfate with copper electrodes, Cu2 plus ions deposit as copper metal at the cathode, and copper anode atoms dissolve into Cu2 plus ions. The overall solution remains unchanged, but copper simply transfers from one electrode to the other. This summary table of electrolytic reactions is your best friend for exams. It condenses the whole story. So, let's wrap it up. Electrolysis is not just some bubbling solution in a beaker, it's everywhere around us. It coats metals in protective and decorative layers, purifies impure ores into shining metals, and extracts elements too stubborn for ordinary chemistry. From silver-plated jewelry to copper wires, from aluminium foils to hydrogen fuel, electrolysis is quietly powering the world of materials. Remember, the choice of electrode, the type of electrolyte, and the nature of the metal all decide the products formed. Mastering these applications connects what you study in the classroom to industries, technology, and even the gadgets you're holding right now. I hope this session made you see electrolysis not just as a chemical process but as an invisible craftsman shaping the world around us. Until next time, keep experimenting, stay curious, and let chemistry electrify your imagination.